everybody, this video is going to be about salts and how they behave when you dump them in water. We're going to see how the pH will change based on which salt you put into the water. So real quick, what is a salt? Well, we typically tend to think of table salt, right? We think of sodium chloride, but sodium chloride is just one of many salts. Salt is a category that covers lots of different compounds. So a salt is an ionic compound that's formed when an acid and a base react with each other. For example, if we have sodium hydroxide and hydrochloric acid, we get water and what we think of, right, as table salt, sodium chloride. So that's just one example. Here's another example. You see that you still get water and you get a salt compound. So when you put a salt into water, what ends up happening is that they dissociate. The ions are going to separate. They're going to break apart. The thing is that when they break apart, sometimes the ions that form are going to react with the water molecules and a reaction is going to occur. So once they've dissociated, that reaction with water we call hydrolyzing. Sometimes the ions will hydrolyze. Not always, but sometimes. Here's an example. You can see that the water took one of the hydrogen off, right? And it made a hydronium ion. The thing is that the ions need to be strong enough in order to rip off a hydrogen from a water molecule, or they need to be willing to give up a hydrogen so that it can make a hydronium. Not all salts are going to be able to do this. We're going to have to know if the ion will hydrolyze or not. The result of an ion hydrolyzing is that the pH is going to change. It's going to end up turning the water into something that's acidic or basic. If hydrolyzation doesn't occur, you might end up with something that is neutral. Here are some examples. You can see the water took off one of these hydrogens, and the resulting solution would be acidic. Compare that to this. The carbonate this time is going to take off a hydrogen from the water. That's going to result in a hydroxide being left over, and so your solution will end up basic. Something like the chloride ion is not going to be able to hydrolyze. It's not strong enough. And so when you're done, you really don't have anything different, right? So your solution is neutral. It did not hydrolyze. So we have to know, well, is it going to hydrolyze? How do I know if it's strong enough? And there's a pattern. So what you're going to do is you're going to have to think about where the ion came from. If you can figure out where the ion originated, you can think about the properties of that molecule, and it will help you figure out what the properties of the ion will be. So let's look at some examples. If we had a strong acid, what's going to end up happening is that strong acid is going to dissociate, and the ions that you end up with are going to be weak because most of the molecules want to be dissociated because it was a strong acid. The resulting base is not going to want to go back to where it started. So a strong acid will result in weak ions, and it will not be able to hydrolyze. If you have a weak acid, the ions are going to be strong base ions, and they will hydrolyze because they don't want to be in their ion form. They want to go backwards, and they want to steal a hydrogen from a water to go back to be the acid form. Right? A weak acid means it doesn't dissociate very much. A strong base is going to want to dissociate a lot, And so the ions that it turns into will be very weak acids. They're not going to be strong enough to hydrolyze. A weak base is going to have strong acid ions, and that will hydrolyze. So what you can see is that if you originated from a strong acid or a strong base, your ions are going to be too weak to hydrolyze. They want to stay as their individual ions. However, if your ion came from a weak acid or a weak base, they don't want to be in their ion form. So they're going to go around ripping things off of the water or donating things to the water, trying to get back to their weak acid or base format. And so those strong ions are going to be able to hydrolyze. They're going to react with the water. So thinking about why does something strong turn into weak ions or vice versa is because we have to think about where that equilibrium lies. If you have a strong acid, almost everything is going to dissociate. It's going to lay very heavily to the right-hand side. It wants to be in its ionic form, right? It wants to have these ions here. If it wants to be broken into these individual ions, why on earth would this chlorine try to bond with a hydrogen to turn back into hydrochloric acid? It's not going to want to do that. The chlorine is want to just float around by itself. It's going to ignore the water. So you're not going to end up with any hydrolyzation happening. This can be pretty tough for people because this requires that you know what your strong acids and bases are and that you can recognize their conjugates. So one of the few times in chemistry where I think good old-fashioned, flashcards are really helpful, you have to know your strong acids and bases. Otherwise, you're never going to recognize what a conjugate is. You're never going to be able to decide if it's strong or weak. So please, please, please work really hard to memorize those. The other thing that I notice over the years is that people have a tendency to try to do this all in their head, and then they end up really kind of all jumbled up and confused. Just take 10 seconds and do some scratch work on your paper. I think it really will help you. Okay. So, how we predict the pH. Let's kind of walk through the steps you would have to do. First, you need to identify the acid or base that the salt ions came from. Where did they originate? Which acid did the anion come from? Which base did the cation come from? Then, once you know where they originated from, you'll be able to figure out if those ions will hydrolyze or not. So, if they came from a strong or weak acid or base is what you're trying to figure out. You figure out in step 1 where they came from. Then you're asking yourself, was the original molecules, were the original acids and bases strong or weak? If the ions came from something strong, they will not hydrolyze. If the ions came from something weak, they will hydrolyze. If something is going to hydrolyze, then you're going to try to decide, okay, which one is going to hydrolyze? Will it make it acidic? Will it make it basic? How is that going to work? And that's where you're kind of using this little chart. If you have your weak conjugate base, the ion will be neutral. If it was a weak acid, you have a strong conjugate base, so it's going to end up basic. It'll be a basic ion. Weak conjugate acid, be neutral. Strong conjugate acid will be acidic. Next, you have to remember that you don't just have one ion present, you have two. And you have to see what the combination of those two ions would be. So for example, if you had two neutral ions, your solution will be neutral. If you have neutral and basic, it'll end up basic, right? You're going to have to kind of walk through those combinations and see how they're each contributing. If you have an acidic ion and a neutral ion, your final overall solution will end up acidic. If you have a basic ion and a neutral ion, you end up basic. If both ions are neutral, they both are weak, they both came from strong acids and bases, they do not hydrolyze, you'll end up with a neutral solution when you're done. The hard ones are when one of your ion will be acidic and one of them is going to be basic. And when that happens, you have to figure out who wins, who's more acidic, or which one is more basic, right? You're going to have to compare your equilibrium constants. You're going to have to compare your Ka and your Kb to see who wins the reaction. So let's kind of walk through that part a little bit. If you have a solution where you have an acidic ion and a basic ion and they're both going to hydrolyze and you're trying to figure out who wins and is it going to end acidic or is it going to end basic, you're going to compare the Ka and the Kb values. Whichever one is a higher value means more dissociation, which means that one will contribute more. So if your Ka is bigger than your Kb, you'll have more hydrogen ions that have dissociated, and so that will end up acidic. If your Kb is larger, you'll end up basic. If they equal each other, which is not common, but it could happen, then it will end up neutral because all of your hydrogens and all of your hydroxides will cancel out. So you'll end up, neutral back again. There is one little twist that they like to throw at you, which is kind of, just a little bit awful because if you don't notice it, you're going to make a common mistake. You don't usually have Ka and Kb values for all the different conjugates that you want. So sometimes what you're going to have to do is you're going to have to remember to convert it. So if they give you the Ka of what you start with, you're going to have to convert that into Kb. Or if they give you the Kb for the base that you started with, you're going to have to convert that into Ka for your conjugate. So you have to pay attention to which values they're giving you, and you have to remember how the Ka and the Kb are related to each other. So if you remember from our ionization of water, right, this is the equation that we like to use to convert back and forth. If you want the Ka of your conjugate ion, you need the Kb of the base it came from, and then you can convert. If you want the Kb of your ion, you're going to take the Ka from its original acid and convert it. So let's do an example. Let's say that you need the Ka value for this. Right? You need to know what that Ka is, but I didn't give it to you. Instead, I gave you the Kb of the base that it came from. It came from ammonia, didn't it? I told you your Kb of ammonia is 1.8 times 10 to the minus 5. But you're not dealing with ammonia, you're dealing with the ion, its conjugate acid. So plug it into the equation up here and solve for Ka. You should have memorized what Kw is. So give that a try. Try to calculate what your Ka of your conjugate acid ion would be. Let's see, you plug that in, you solve for Ka of your conjugate acid ion, and that's the value that you would be able to use when you're doing your salt problem. Let's do a couple practice problems. We're going to kind of walk through some examples that we might see. And you'll be able to kind of see the thought process as I go through those steps I showed you earlier. So practice problem number 1. What I've done is I've put the little chart at the bottom so that will make it easier for us. Now realize on a quiz and a test you won't have access to this chart. You'll have to know how the pattern goes, okay? But in the beginning it's totally fine to look at while you're learning. So the question is going to ask you something like, is potassium bromide an acidic, basic, or neutral salt? If I dumped that in water and I took the pH of the solution, what would I see? I have to identify the ions that are present and where they came from. So potassium is going to come from a strong base, potassium hydroxide. You have to know your bases well enough that you will notice that, right? So if potassium came from a strong base, the resulting ion, right, the potassium itself will be a weak acid. It's not going to want to go backwards to KOH. It's going to want to stay like this. It does not want to react with water. It wants to be left alone. No hydrolysis. So the potassium is going to have a neutral effect on the water. Bromide, well, there's a strong acid that has it, right? If bromide came from a strong acid, that means it wants to stay as a bromide. It wants to stay dissociated. So bromide is a weak base. It does not want to go backwards and steal a hydrogen off of the water. It does not want to react with water. It wants to be left as bromide. So no hydrolysis. So this is a neutral effect. So you can see that I have 2 ions that both have a neutral effect. So then I'm going to think about how those will interact with each other. How do they both contribute? Well, if I have neutral and neutral, you end up with neutral, right? So potassium bromide is a neutral salt. So once again, I took the compound, I figured out what the ions were and where they came from. I decided if they were strong or weak acids and bases, where they originated. That told me what the ion behavior would be, and I could decide if it hydrolyzed or not. And then I can see what those effects would be combined together. All right, let's try another one. Number 2. This time is potassium carbonate acidic, basic, or neutral? We need to think about our individual ions. If you don't recognize polyatomic ions, that's going to be tough, right? So now we can say, well, okay, potassium. I know that there is a strong base that has potassium in it, potassium hydroxide, like we just did on the previous slide. Because potassium hydroxide is a strong base, the potassium is going to want to be just, an ion floating around. It does not want to go backwards to potassium hydroxide. So potassium ion is a weak acid, no hydrolysis, neutral effect. Compare that to carbonate. Carbonate comes from carbonic acid, right? H2CO3. Well, carbonic acid is not a strong acid. It's a weak acid. So if this is a weak acid, most of those carbonates are going to want to be in this format, aren't they? They do not want to be dissociated. So this poor little carbonate ion is going to go around ripping hydrogens off of the water, desperately trying to get back to this form. Carbonate does not want to be by itself. It's desperate to look like this over here with the hydrogens. It's desperate to be an acid. And so it will rip hydrogens off of the water, which is hydrolysis. If it's taking the hydrogens away from the water, then there's hydroxides left over. So it will have a basic effect. It will result in hydroxides floating around. It's not that the carbonate ion itself has hydroxides to contribute. It's that the carbonate ion steals the hydrogens away from the water, which leaves basic hydroxides floating around. So now let's think about how these two things combine together. If I have something that's neutral and something that's basic, I will end up with extra hydroxides at the end. So potassium carbonate will result in a basic solution. If I took the pH of potassium carbonate dumped into water, it's going to show a basic pH. Potassium carbonate is a basic salt. All right, I'd like you to try number 3. Ammonium bromide. Is it acidic, basic, or neutral? I would like you to pause the video, try to figure out the ions that are present, figure out where the ions came from, decide if those original acids and bases were weak or strong, decide if that makes the ion a weak or strong conjugate, and what the effect would be. So pause and walk yourself through this problem. All right, let's see. Well, here are my ions. Ammonium came from ammonia, which was a weak base, which means that this must be a strong acid. It does not want to have that 4th hydrogen present. It wants to get rid of it. It desperately wants to look like the ammonia. So that makes it a strong acid. So it hydrolyzes and will end up acidic. Bromide came from hydrogen bromide. Strong acid. It wants to be dissociated. Bromine is weak. It wants to be left alone. It does not want to react with the water. It will not hydrolyze, so there will be a neutral effect. So if I combine something acidic and something neutral, I'm going to figure out that my salt was acidic. All right, let's do one more. Get to the point on this slide where you know if your ions are acidic or basic, and then pause, because you're going to get to a point where you need a little bit more information. So give it a try. Try to figure out if it's acidic, basic, or neutral. Each of those ions. All right, well, these are the ions that we have. We just learned that this started out as ammonia, right? Which was weak, which makes this strong. It would like to have an acidic effect. It would like to hydrolyze. This is the cyanide ion. Hydrogen cyanide, right? That's weak, which makes the conjugate ion a strong base. Wants to hydrolyze, so it's basic. Well, now we're in that situation where one thing is acidic, one thing is basic, and we don't know who wins. Which is stronger? Is the acid stronger or is the base stronger? Or are they equal? We need some K values. So, here's the Kb for ammonia, and here is your Ka for your hydrogen cyanide. But you should notice, those are not the things we're comparing, are we? We are comparing the ions. So I don't want the Kb. This is an acid. I need the Ka. Cyanide is a base. I don't want the Ka of this, I want the Kb for the ion. So you're going to need to convert them. You use Kw and the Kb of where it originated, and that will give you the Ka for your cation. You need to use the Kw and the Ka for where your ion came from, and that will give you the Kb for its conjugate. If you calculate those out, these are the values you get. Now, would it be nice if they gave them to you all in one big giant chart and you never had to convert anything ever again? Obviously, that'd be nice, but that's not real, okay? We rarely are going to have a chart that has the ions listed. So, compare your Ka to your Kb, which is bigger. Your Kb value is bigger. That means that that cyanide is more basic. It wants to be dissociated more than the acid does. Therefore, base wins. Your salt was basic. Now, it gets a little bit tricky if I ask you to go one step further. What if I don't just want to know if it's acidic or basic, but what if I want to know the actual pH when I'm finished? When I've dumped everything together, will it be acidic or basic or neutral? And what will the pH be? So switching gears a little bit, let's talk about calculating what the pH might be. You have to do all of the steps we just did. Then what you have to do is you need to write out the chemical reaction for the ion that hydrolyzes. You need to actually write out the ion plus water is going to turn into what? And then everybody's favorite thing ever, back to ice tables, right? We're right back to those ice tables. Hydrolysis is a equilibrium. Right? You can go back and forth. It's reversible. You have to figure out how much is going to be, hydrolyzed when you're done, when you've reached your equilibrium point. So you're back to using your ice tables. You are not using the ice table for the dissociation of your salt. You are using the ice table for the hydrolysis of the ions reacting with water. So be careful about that. Once you have your ice tables, you can figure out what your concentrations are, and then you're doing normal pH calculations. So this topic of calculating the salt pH is just mushing together 3 separate things we've already learned how to do. You know how to do a normal pH calculation, you know how to do ice tables, or I guess 4 things, right? You know how to write a chemical reaction, and we just learned how to figure out if something will hydrolyze or not. So let's do one of these practice problems. What is the pH of a 0.25 molar ammonium nitrate salt solution? You need to decide, is it acidic, basic, or neutral salt before we begin. So you need to get all that figured out before we do our calculation. Right now, why don't you try to do that? You decide, will this solution be acidic, basic, or neutral? Pause the video so you have time to do that. All right, so these are the ions that we have inside of our salt. Let's think about where they came from. Ammonium came from ammonia, which is a weak base, which makes the conjugate ion strong. It will hydrolyze. It's trying to get rid of that 4th hydrogen. It doesn't want it. It wants to be in this form. That will result in extra hydrogens floating around. It'll be acidic. Nitrate ion came from a strong acid, didn't it? so it is weak. It's not going to hydrolyze. It wants to be left as a nitrate ion. It is not going to go around stealing hydrogens from the water. It's going to just float around minding its own business. So it will be neutral. Well, if I have an acidic ion and a neutral ion, my resulting solution will end up acidic. So what I'm going to do now is I am going to try to figure out how acidic will this solution be. What will my pH be when I'm done? I'm going to need K values to do this, right? I'm going to need a hydrolysis reaction to do this. So let's take this acidic ion, this strong ion, and react it with water. My ammonium ion is going to hydrolyze. I take that ion, I react it with water. What happens? Well, it gives away one of its hydrogens. I end up with ammonia, and I end up with a hydronium. That's acidic, right? Because I'm doing something with an acid, I need a Ka value for this. I'm trying to see how acidic is this thing. I need a Ka. I don't have a Ka. I just have a Kb. What do I have to do? Well, I'm going to use my equation. I'm going to plug it in, and I'm going to solve for the Ka of that conjugate. Why don't you go ahead and try that? All right, you end up with this as your Ka value. Now that you have concentrations, now that you have a chemical equation, and now that you have a K value, now you can finally do your ice table. Do you remember when I was telling you that you had to be fast at ice tables? Do you see why? Ice table is a baby step here, right? It's just one of many steps we're doing. So when we set up our ice table, we will use the hydrolysis equation. To save time, I just plugged it in for you. Let's talk about it. The initial concentration matched up here, right? Because when this dissociates, if I started with 0.25 molarity of this whole salt, I'll have 0.25 of the ammonium. Remember, water is a liquid. We don't care about it. You don't have any products when you start. You just put zeros. It's a 1-to-1 stoichiometry ratio, right? So this will be minus x and plus x. We're going to use the 5% rule. This simplifies this down. You have your Ka value. So let's write a K expression. Let's write that law of mass action. Products over reactants. Careful if there were any coefficients that you need to put as exponents, right? Don't forget that. Set that equal to your K that you already calculated on the previous slide. Plug in your 5% row. Solve for your X value. And you now know what the concentrations of these products were when you were finished. Now look at what those products were. Okay, one of them was my ammonia. That's weak, not really doing much for us there, right? Oh, look, here's where the acid comes from, right? So now that I have a concentration for my acid, now that I know those hydroniums, right? I know how much of that I have. Now I can do my pH calculation. pH is negative log. You get your final answer. Now, just to compare, if you were to take the negative log of 0.25, you should see that you get a pH of 0.60. You get a really, really low pH. Well, that doesn't match, does it? Because not all of that is going to turn into, acid. That's why we had to do the ice table. That's why we needed the K value. Not all of it dissociates. Not all of it ends up causing that hydrolysis, right? And so you can see that while it's still acidic, it's not as acidic as if you just plugged in that 0.25, because that's the concentration of your ions. That's not your concentration of the hydrogen ions after the hydrolysis reaction. So you have to be really careful that you're not on autopilot and you see pH and you plug in a number. You have to notice if it's a salt or not. Then you walk through all those steps that we learned. Then you do an ice table. Then and only then do you get to do your pH calculation. Some of the longest problems we will do all year are salt pH calculations. It's important to get good at salts because they're very, very common in AP chemistry. We do a lot of things with acids and bases. We do a lot of things with salts. So we like to end the year with this topic so that when you start AP Chem next year, it's going to be hopefully as fresh in your mind as possible. All right. That's it for this lesson. I hope that was helpful. Bye, everybody.